Quinson.
Thank you for the introduction. Hello, I'm Quinson Hon. I'm a student in CUHK who has worked with GraphRAG systems before. So today I'll be talking about some of my experience, some of the basics, and some experience I've had with GraphRAG with using Python and also Neo4j. So just a bit of a just a bit of a recap for people who aren't as familiar with RAG. So I'm sure everyone has used LLMs before, talk to ChatGPT or use Sonnet or that kind of thing. And the problem with these large language models is that they often struggle with very domain-specific knowledge. So they're very good at stuff you can find online. But when it comes to stuff that you have owned privately, for example, if you have some notes lying around at your home, or you're working for a company and you have a lot of company documents, or specific laws, or knowledge about niche topics, large language models tend to not perform very well because they're trained to remember like the breadth of data rather than going very deep into things. So that's why we would need some additional help for them to do better in these aspects. They can also hallucinate, provide information that is incorrect, and also they have a limited context window. So even if you have like a huge document, a huge set of documents, you can't just throw everything at the LLM because there's a context window, and if you put too much context, the LLM struggles to find the things that you need. And that's why we need Retrieval Augmented Generation. So the LLM can read specific parts of your data that are useful for your question to answer questions. Okay, just do that. Okay, so in RAG, what you would tend to do is you would turn text into chunks and then convert those chunks into vector embeddings, which is basically a list of numbers using an embedding model. And then you store them in a database somewhere. And then when you query, you also take the string of text that you query and you turn that into embedding, another list of numbers. And then based on these numbers, you do some simple calculations to find the most similar vectors. So basically, you multiply the two vectors and add the terms up. If the number is highest, then it represents some sort of most similar. There's some idea of being most similar to the query, and thus you can extract the chunks and then put them into LLM as context. And the problem of that is that when you divide, part of the problem comes from having chunks instead of entire documents. By doing that, you treat data as isolated snippets and don't think about the relationships between them. So what you end up doing is you miss out on rich connections between entities and other objects. And in some cases, when you're working with more structured data, but that's also highly connected, like social networks or transactions, you would tend to miss out on these connections if you just use chunks and embed large sections as is, which is why we have GraphRAG. So GraphRAG enhances traditional RAG techniques by leveraging graph databases to understand and use relationships between these data points. So instead of getting chunks, you retrieve nodes, which represent entities. Could be a person, could be an object, could be a concept, and you represent them as nodes with different properties, and then connect them with edges, which are also relationships, so that you can encode the relationship between objects and not just the objects themselves. So this gives them richer context and for accurate, relevant responses, and also ideal, which is great for when you have lots of connections to deal with, like knowledge graphs or complex documents. So today I'll be going through some of the ways you could interact with Neo4j, which is a graph database, with Python, how you could build some RAG pipelines with it, and also building knowledge graphs based on documents. So to create a Neo4j database, you have two options. You can use their cloud service, which is Neo4j Aura, and there's a free tier available and there's also enterprise options as well. You could also try it yourself using a Docker container, and this is just a command that I took from Neo4j. You can just run the Docker and you will have an instance. one thing to note is that you would, and if you want the data to persist, you would want to store it in a volume so that the data can stay there and not get reset every time you run the Docker. Okay, so to connect to Neo4j, you need a URI, like an address to access the database, and you also have need authentication, basic authentication. So you have a user, password, and then you create a driver instance, which is the thing that interacts with which is the software component that interacts with the database. So, and Neo4j uses a language called Cypher, which is a querying language kind of like SQL, but for graphs. And so you can create nodes and relationships within a Neo4j so that to store them directly, and then you can ask questions about it. So for example, here we have some create statements. You have these identifiers like P1, P2, P3 for how you would refer them in the query, and you can assign a label like a person, and then also some properties such as name or age, and then store the values, and the same thing with relationships, which is done using like this syntax right here with square brackets instead of curly brackets for nodes. And you can specify properties and also give relationships types as well. So let me show you this. So I can just copy this, and I will see if this works. Okay, so here's what it would look like in actual code. Here's what it would look like in actual code. You define some URIs, user passwords. So let me just run this. Okay, and then here I can put the query in, and then after you put the query, you can, okay, let me fix this real quick. All right. So you have this, and you create a session with the driver with the database name, and then you use the run method to run the query and then get the data back. Now let me run this, and it says nothing because I didn't return anything in the query. So if we look at the Aura instance, here, here's the nodes. I forgot to get the relationship as well, so just bear with me here. So here, if you want to get the information, you can use the match. I will explain this a bit later. So you have this. So now, after creating the nodes and relationships, it will show up in the graph right here. And here, as you can see, the attributes are here on the side, whereas here you have a visualization of the graph as you update it and as it returns to you. And so we have attributes in the nodes and also attributes in the relationships. So that's how you create them. And then you can do some simple queries, such as in this example where you just asking what nodes have the label person. So in this case, so I can just do this. I can just copy this here, and it will return. Okay, wait. So we have this. So here it will return things, and it will return everything. And since here we use an order by, it will order them by age in descending order, and the columns will follow the naming scheme here. So here we have returned some stuff after that. And you can also do relationship queries by just doing, and some filtering by doing this. Here we are looking for a person named Alice, a node with the name Alice, and that connects to and we're looking for relationships that point from Alice to other nodes. So here, if we do this, we get Alice met Bob, which is what we have here. Now this one isn't retrieved because this is pointing from Charlie to Alice, not from Alice, which is why it didn't pick up this relationship. But that's okay because this is what we want connections from Alice to Bob. Therefore, from Alice to other nodes. So this is okay. And to modify the graph, you would have these set command. You can use the set method or keyword to change some properties. So here I'm doing both edits in the same time. You probably want to do it one at a time if you're actually working with it, but here we can try this as well. And yes, copy and paste does that sometimes. So here we change the person's name from Alice to Alicia, and change the relationship from a relationship property from 2020 to 2023. So here, if you look at before, this was 2020. So if I put this here, if I run this again, now this is called Alicia now, and the attribute changes to 2023. Okay. So finally, to end the first part, we can remove some properties or things from the graph as well. With the remove keyword, you can remove attributes that were there for either a node or a relationship. Either way it works. So if we run that and then run this again. Now, let's see. All right, so we have this one. The in attribute is gone now, and then we can delete entire relationships as well. So with the delete keyword. So now if I run this again, it will be gone. So the connection between Alicia and Bob is gone. And finally, if you want to delete a node, you want to use detach delete, which means the word detach means that you're removing all relationships. You remove all the relationships surrounding that node, and then delete deletes the node. If you try to do that without detach, it will just stop you basically. So if I do this, and I run this again, now it's only 2 nodes. Okay, so that's how you do it so that's most of the main things that you would need if you're interfacing with Neo4j directly. You can just use Python drivers to interact with Neo4j. Just now I was using session run, which is like the most basic form. You can also do more complicated stuff, like use session.execute write or execute read to run more complex queries, and especially to provide parameters. So you have these parameters here, and then those can go in here, which are to make them parameterized queries, so it's more secure and you'll have to worry less about injections and that kind of thing. So yeah, and then in this case you have this function that runs this query and just returns the result. So this is just another way that you can write it if you have parameterized queries. You can also use execute query, which you can also use execute query to just run the query without having to define a new function. And same case for read, you can use execute read to do the read all of the data. So that's the first part done. Next I'm gonna talk about how we do retrieval augmented generation. Okay, let's see. Something.
You want just mirroring?
Should be mirroring.
Let me do it.
Let's see if this works.
What the hell?
Not sure what I touched just now. Okay, seems okay. All right,
Okay.
let's move on. All right, so just now I was going through Neo4j, how to use Python to interact with Neo4j. Now we're going to talk a bit about retrieval augmented generation. But so here, what I'm focusing is assuming you have a graph already that you have created either as a knowledge graph, which I will talk about later, or if you have a structured graph already inside Neo4j, then you can use it. You can do retrieval augmented generation with it. So I'm going to go straight to this slide first. So how it works? So one of the ways to do this is a thing called vector cipher retrieval, which is basically you use vector retrieval to get some nodes and then run cipher queries to get additional information before you give it to the LLM for answering. So to explain a bit more, so here you have you have a query, and then you embed the query with an LLM, so it turns into a list of numbers like this. Turns into a list of numbers, and then you compare this list of numbers with entity embeddings. You can define it however you like what type of data should be encoded into this, and you get vectors on them. And then you compare these vectors with your query vector, find the top k most similar results, and then based on those nodes, you run a cipher query to extract the environment around it. Or you can do some extra stuff because it's just a cipher query. You can find like what's happening in between them or something like that to get some local graphs. And then Neo4j returns the graphs, and then you can parse them again to pass them to an LLM and then answer the query. So before you go to actually doing RAG, you have to index the nodes. So here you have an embedder, which is in here I just use sentence transformer, so you can run it locally, and you create a vector index. Neo4j GraphRAG has pretty good support for these basic operations, so you can just create these. Down internally, it's just running another cipher query, but it's abstracted here, so it's a bit easier to manage. And then here I'm extracting all of the element IDs for the nodes that I'm going to encode, and also returning the thing I want to store in my embeddings, which is the plot or the story of a movie. And here we run embedder.embed query to convert them into vectors, and then we use this method, observe vectors, to upload them to the database. And that just creates the vector database based on your graph. And then after that, you can use a retrieval query so that node score is basically the nodes and the nodes that are retrieved by the retriever based on scoring. And then it will, based on these nodes, it will run additional cipher queries to extract everything around it. So in this case, you're getting the actors for the movie, director, genre, etc., and then you group them together here, and then this result would be passed on to the LLM. So we have and then we just define a vector cipher retriever based on using our driver, the index name, the index for the vector index name, the retrieval query, and the embedder to embed the query text. And then you can just use the search method to get the results. And also you can specify some extra parameters like top k here. Another type of retrieval that might be better if you're using for more structured graphs, or like if you upload everything with Neo4j instead of a natural language, is text to cipher retrieval. So in this case, you have a query, but instead of embedding it, you ask an LLM to generate a cipher query, because LLMs are pretty okay at generating database queries for cipher. So you can ask an LLM to generate a cipher query, and then it will send that query to the database and return results based on that query, and then use that as answering. So in this case, you would have to give them a schema. I forgot to include the schema here, but and also there's not in space. But you can define a schema which you can just tell the LLM, basically just tell the LLM what the graph contains, like what nodes, what labels, what relationships and types there are. You also give them some examples so it knows like what to output, like these cipher queries here. And also you provide it with a driver and a decoder LLM, like you can just plug in like ChatGPT or any LLM you fancy. So, and then after that, you can just use the search method to get results. These results are like the things that LLMs read to answer questions. So we're not at the point where it's generating answers yet, but we're getting there. Yeah, so we have that, and then finally to do fully to do GraphRAG, we just need the retriever and then an LLM that can turn the information it gets into a fully a conversational answer, and again use the search tool, use the search method to get the query text and retriever and pass in extra configs that you need and get the answer. So I will demo this. I can demo this as well. So here we have the previous example I'm always using RDB. Now I'm going to use the Docker container for Neo4j. So here we reconnect, and right now this is a different data store that stores like IMDb results. So it could be movies, it could be drama series, etc. So here I define a retrieval query. Basically, it's just trying to, here we have some subqueries that get extra information about a node and return a bunch of information here. So we run this. And here we define the embedding. You can also define a retrieval result item to format the return data from Neo4j into a format that LLMs can understand. And we define a retriever, and we define an LLM. Here I'm using I'm using an open source model, GPT open source 20B, and we put this into the GraphRAG pipeline and also the retriever up here with the query and the index. I had already made the index before, which is called movie plot embeddings. So we just use that, and we can use it to answer questions. So here we define them. Might take a little bit of time, probably to load to the index. Okay, and then here we have some example questions like, what science fiction movies are there, or I'm looking for a thriller with twists. So here we can run this, and then you use the search query that we was using. So here it gives some answers based on the context, and then synthesizes an appropriate answer here. Yeah. And because we use retrieval results, the context can be formatted properly as well. And here we also have extracted some context and answered to a question about like what movies are thrillers with unexpected twists, and it has recommendations on that as well. So yeah, here's another examples, and yeah, this is just to emphasize that basically you can just feed it. Once you have everything set up, you can just send it a query, put it through this function, and it'll give you some reasonably good answers. Now, one thing to note here is that since the index we used only looks at plot embeddings, it doesn't look at any other information. It might have some issues if the questions are not about the story. So in this case, you have what movies are directed by Christopher Nolan. The thing is, this is encoded in a different property in the nodes. So, but our embeddings only contains information about the story. So in this case, even with a very high top K, it will just say none of the films listed in the context are directed by Christopher Nolan. So this is one thing you have to be careful about. You have to manage like what to embed with nodes as well. So there's that. Okay, so we've talked about RAG, but we haven't talked about how to create the graph from natural language yet. So the steps before is what you would do if you could format it in a way that's suitable for a graph. But if you have just text, then you need an extra step to create a knowledge graph. So I'll go here. So a lot of the steps are quite similar to standard RAG. So you have documents, you chunk them with any chunking method that you like, turn them into chunks. And then here you have chunks, and you put them through a data processing. You put them through a language model with like stuff like ChatGPT, and prompt it so you're telling, hey, I have this block of text. Help me find what entities and relationships are in this block of text. And this extraction step will return you want to tell it to give it a JSON object so that it can be further parsed and processed so that Neo4j can use the information to create graphs, and create a graph, and so you can do more stuff with it. And after creating the graph, you want one thing that you should probably do is entity resolution. And this is a step where if you have two different chunks and they contain the same entity, when you create the graph separately, there will be two nodes of the same thing but are disconnected. So but they refer to the same thing. So what you want to do is to merge them somehow, and you can do some, and then Neo4j does some stuff under the hood in their Python methods to merge the nodes together by name, or you could define some custom functions to merge them more properly, something like that. And then after that, you will get document graphs. You will get the graphs. And finally, once you have the graphs, you can compute the embeddings with an embedding LLM, and then turn them into embeddings. Now, I think in Neo4j GraphRAG, it only does it on chunks. I could be wrong about I'm not sure if it does it on entities, but by default, I think it does it on chunks. But you also wanna, if you wanna search on entities, you wanna also include entity search as well. You want to make entity embeddings as well. So once you have, so with that in mind, you can make some. You can make a knowledge graph. So you could define some text, or you could feed it a PDF, and then just give it the LLM, the driver, and then embedder. The LLM is for finding the entities and relationships, and the embedder is for embedding the nodes. And to do that, and then you run it, and you'll get a knowledge graph inside the Neo4j database with some connected information. After this step, you probably want to do some additional operations to make it more interconnected, but I won't go into details here. And creating a knowledge graph tends to be like the most tends to be the most costly part of the entire process. So you want to test it on small things first, and also just be wary about it, and just be wary about like how long it might take. This is like the most time-consuming part, because you have lots of documents. Each chunk has to be passed through an LLM to create to create graphs, so it's a bit time-consuming. But after that, after doing this once, you can search up the entire database, so it's worth it. So so that's most of the details I want to cover today. I'll just wrap up with a few things to be careful about when you're making pipeline. Chunking strategy matters, obviously. You have to define the chunks. Better chunking will give you more coherent results. Extraction prompts, you can try to tune them. You can also specify a schema for extraction, so you can tell it to say, hey, only extract like certain types of relationships or certain types of nodes. The LLM for extracting should be good enough at JSON output, so you might want to play around with it. And preferably you want to try not to choose something too expensive, because the prompts are quite long and you have a lot of documents, so just think about it. So just be careful of that. And also the entity resolution step, which I've mentioned already. Now, in the retrieval step, you want to look at retrieval methods. So I went through vector cipher retrieval and text to cipher retrieval. The Neo4j also provides full text search, and it's also implemented in the Neo4j GraphRAG library. So you can use that. You have to be careful about embedded information in nodes, which I've mentioned already, about like how it's missing information because you only encode the plot or the story. And you can also have to be careful about what LLMs you're using, what cipher query you're using after node retrieval. So like how big the graph, how much stuff you want to include from around the node, number of results to retrieve, and also finally the prompt template for the final generation step. So that's some of the things to think about. And so I'll just conclude by saying GraphRAG enhances traditional RAG by using graph databases to understand indices and relationships, and Neo4j is a good tool for that. There are the Neo4j and Neo4j GraphRAG libraries can simplify building these pipelines to a few simple steps. You can use it to build knowledge graphs and leverage Python's natural capabilities in AI to complete various tasks in GraphRAG, and ultimately you can change it in any way you like to fit your specific use case. So here are some references. I find the documentation examples from the GraphRAG package are pretty useful, and some documentation on the driver. If you want to go deeper into more complicated methods like global GraphRAG, where you have more holistic, where you want the LLM to have a more holistic view, this book, this has some interesting code and goes a bit deeper into how these operations work. And finally, I also have a repository for this talk, and I've uploaded the slides and also some example code that you can play around with. So that's about it. So if you want to know more about me, here are my links. And I'm just a guy who messes around with AI quite a bit. So if you want to talk now or a bit later, you feel free to hang out outside or just contact me through. You can find other contacts on LinkedIn. So that's about it. Thank you.